Good education also.
It is my very big pleasure to welcome you all on this online defense of Margarita Bulatova. And the opponent will be Professor Catharine Esterhuysen from Stellenbosch University, South Africa. And if some of you know me, you know that I'm not Matti Haukka, so official supervisor of Margarita's thesis is Matti Haukka, but he was not able to come, so I'm his substitute and act as her official Custos of this defense. And now, as the Custos appointed by the faculty, I declare this defense open.
Right. So, distinguished Custos, honored opponent, ladies and gentlemen, sorry? Mike. Oh. See? Too nervous. Try to put it on. Okay. And oh. So I will start from the scratch. Again, distinguished Custos, honored opponent, ladies and gentlemen, I'm really happy to welcome you today here on my PhD defense. And I'm Margarita Bulatova, and I will be talking today about non-covalent interactions. Sorry, this is supposed to be as a force for supramolecular self-assembly of metallopolymers. And as today is a very, very special day, I have to say, may the force be with you. So this doesn't work. Okay, now works. Yeah. So I will start from far away, talking about what is chemistry. And it is important to say that it is a science that deals with the composition, structure, and properties of substances, and with the transformation that they undergo, at least according to Merriam-Webster dictionary. So in chemistry, we scientists try to create something new from something old. And for this purpose, it is really important to understand the interaction between species, so then we can create some new materials. So what is an interaction? According to the IUPAC Golden Book, when forces acting between two atoms or groups of atoms lead to the formation of a stable independent molecular entity, a chemical bond is considered to exist between these two atoms or groups. In other words, if an interaction has physical consequences, it does exist. So how do we distinguish interactions? So just imagine we have two species and they're interacting somehow. So we can try to measure this interaction with a unit called interaction energy, which is measured in kilojoules per mole. There is a certain scale of this interaction energy, and we can locate different interactions on it. So non-covalent interactions are actually the weakest, and they're from like 0 to 100 something kilojoules per mole, and covalent interactions are a bit stronger, much stronger, and they're from tens to hundreds kilojoules per mole, while ionic interactions are actually the widest on the spectra interactions, starting from tens and ending up in thousands of kilojoules per mole. But in my research, I was interested in non-covalent interactions and utilizing them to create new structures. So non-covalent interactions, those are weak in energy, but very strong in unity. And the non-covalent force I was trying to apply was halogen bonding and its collaborator metal-involving interaction. So halogen bonding was the main force that I was trying to utilize. And according to IUPAC definition, a halogen bond occurs when there is an evidence of a net attractive interaction between an electrophilic region associated with the halogen atom, fluorine, chlorine, bromine, iodine, in a molecular entity, halogen bond donor, in other words, and a nucleophilic region in another, or the same molecular entity, if the molecular entity is flexible enough. So on this slide, you can see that there is this Rx, and it's actually representing the halogen bond donor. And it has this reddish point, which is called a sigma hole, a region of positive electrostatic potential. So it can really interact with the nucleophile, or this Y species that is shown in there, and create this interesting non-covalent interaction, which is called halogen bonds. So halogen bonding. I was trying to utilize during my research some of its main properties, such as directionality and tunability, and those are closely related to this sigma hole and its size and magnitude, so its properties. So can we really influence the sigma hole? And the answer is, of course, yes. So how do we, well, first of all, the directionality is a very important parameter. So classical halogen bond is considered to be within the 160, 180 degrees. But then this tunability, we can really play around the groups. So first of all, we can play around the R group. So we can have an electron withdrawing or electron donating group in there, and it can either decrease or increase the sigma hole size. Well, we usually prefer to increase it, so then the interaction is stronger. Then we also can play around the halide itself. So we can change it starting from fluorine, going down in the periodic table, ending up with the iodine. And of course, we can also play around the nucleophile. So metal-involved interactions, those are actually great allies in my structures and my research for halogen bonding. What are they? Those are weak interactions that involve metal centers. So they can be polar with clear electron nucleophilic rows assigned to interacting atoms, or non-polar with undefined electron or nucleophilic rows. Well, sorry, my lovely picture covers a little bit of the presentation, but there's several examples of these interactions that are involving sigma holes, electron belt interacting with the metal ion, some cation anion pi interactions, some metallophilic interactions. Non-polar examples represent intermediate metal halogen interaction and some metallophilic interactions. Okay, but also during my research, some other non-covalent interactions were applied, like hydrogen bonding and pi stacking. However, I will not talk too deeply about those today, because main heroes are halogen bonding and metal interactions. So non-covalent force. Sorry, I will just put my picture a little bit further away because it bothers me so much. Yeah, hello. So the non-covalent force, how do we really study it? Well, there are plenty of methods how we can study it, experimental and theoretical. The problem is, of course, I was limited with time, my own skills, some equipment and collaborations. So I had to choose. And out of experimental methods, I have chosen single crystal X-ray diffraction analysis. And this analysis can get the main aspects of the interactions from the structure itself. And then when I already know where to search for and what to search for, I can try to model these interactions using computational chemistry, modern computational techniques. And this can give the understanding of the nature of this interaction, which is important if we want to utilize it further, of course. So when I started to apply theoretical chemistry to learn it, I was really scared, as many students who are getting into this area, because it has a lot of this horrible abbreviations that really scares and panics all the small students like me. So, for example, like this DFT, ESP, NCI, plot, Qtame, ELF, ED, ESP. Don't get technical with me, and I won't get technical with you guys. Yes, horrible joke, but I had to do this. All these methods, although they sound horribly scary, they are not, and they're amazing, and they help us to understand the nature. So then we can utilize and create novel materials. And that was what I was trying to do. So, and again, in this picture, so creating a metallopolymer, how we can really do that? So metallopolymer, the word itself contains a concept of what is metallopolymer. So it is something that contains metal and something that is arranged in a polymeric structure. So in my case, I was utilizing some molecules that are having metals, so metal complexes, and interlinking them with non-covalent interactions. So what molecules did I use? Well, as I was saying, halogen bonding was my first option and the main force. So some halogen bond acceptors molecules, they were acting as molecules containing metal centers and acting as a nucleophile. So the molecules that really like something with a positive charge, let's say so. And the other option was a linker molecule, and that was a halogen bond donor molecule, which was acting as an electrophile. Okay, so the choice of the systems they studied, as I say, I was limited with time, my 2 hands, and some lab equipment. So I had to choose some certain molecules. As nucleophiles, I have chosen platinum cyclooctadiene complexes, platinum palladium isocyanate complexes, and B-imidazole-based organic ligands. From electrophilic point of view, I have chosen some classical halogen bond donors, such as iodoform, 1,4-diiodotetrafluorobenzene, or PHEP, I can call it further like that, diiodine molecule, and potassium iodide. So halogen bonding, it can be really used as a tool for fine-tuning the geometry of a system. So we can create 0, 1, 2, and 3-dimensional systems. So how can we really control this dimensionality? Well, as I say, there are many methods, but I was utilizing 2 tactics. First was changing the halogen bond donor, so this Rx entity. So I was utilizing a diodide molecule, iodoform, and PHEP. And the other one was to change the halide. So in this case, this was done with the platinum cyclooctadiene complexes, and we were playing around iodide, bromide, and chloride version of this complex. So we have managed to achieve 0 and 1-dimensional structures with this platinum cyclooctadiene complexes interlinked with the diodine molecule. And for iodide and bromide version of the complexes, we managed to achieve isostructural complexes, meaning they're really, really similar in structures. And those were like 0-dimensional heterotrimeric structures interlinked by a strong halogen bonding. And in the case of the chloride version of the complex, we have managed to achieve a 1-dimensional chain, also interlinked with a strong halogen bond. In case of 2-dimensional structures, this was achieved with the platinum diodide cyclooctadiene complex interlinked by a iodoform molecule. So a first dimension was created via hydrogen bonding, while the second was created by a set of halogen bonds, strong halogen bonds. Then another set of 2-dimensional structures was achieved with the platinum palladium isocyanate complexes and diodine molecule. Oops. So we managed to achieve, again, 2 isostructural co-crystals, again, as a structure really, really similar in structure. And in that case, the first dimension was created by a set of halogen and metal involving interactions. And the second by a pi stacking, which is quite weak, but together they're making this wonderful 2-dimensional structure. 3-dimensional structures we managed to achieve with the platinum cyclooctadiene complexes interlinked via fluoroiodobenzene molecules. In that case, again, there was an isostructural pair with the bromide and the chloride version of co-crystals. And in all of the cases, 3-dimensional structure was actually created by a set of halogen bonding and pi stacking. However, for the platinum iodide cyclooctadiene co-crystal, we have also managed to find that there is additional interaction stabilizing the structure, which is a metal involving interaction. So, an interesting question. We want to know what is the nature of the interaction so then we can utilize it. Or in other words, who is the donor, who is the acceptor? In case of halogen bonding, it was quite clear because the experiment was designed in such a way that metal complexes were acting as a halogen bond acceptors, and well, classical halogen bond donors were acting as a classical halogen bond donors. But the other question, which co-crystals have halogen bonds that are stronger with the force? And in that case, the answer is, well, using the computational and experimental methods, we managed to achieve, to understand that the weakest halogen bonding was found for iodoform co-crystals, the medium one for the fluoroiodobenzene co-crystals, and the strongest for iodine co-crystals. And this was also in the correlation with some computational data. So we were trying to understand what is the size of the sigma hole, and the smallest one was found for the iodoform molecule, while almost similar in strengths Sigma holes were found for the fluorodobenzene and the iodine molecule. And this correlates with the previous slide. So metal-involved interactions, those are weak, but still supportive and still important. Those were found for this platinum-palladium isocyanate complexes, and as I was already trying to underline, platinum iodide cyclooctadiene co-crystal. So what made us think about this interaction a little bit deeper? So as I was telling you, the ingols are quite important in halogen bonding. So for halogen bonding that we found in these systems, the ingols were within the standard range. So this iodine-iodine contact had this within 160, 180 range angles. But in case of the metal iodide interaction, the angles were much acuter. And due to that, we were really interested, what is happening in there? Is it still halogen bonding or is it something else? So yeah, again, the question arises, what is the nature of the interaction? Who is the donor? Who is the acceptor? And in this case, we performed some computational analysis and as well as some crystallography studies. And we found that in case of the platinum-palladium isocyanate complexes, the interaction was actually very strong. However, still weaker than the halogen bonding. But in the case of the platinum cyclooctadiene complex co-crystal, the interaction was much weaker, still supporting the total structure. Okay. And the other important question, so who is the donor, who is the acceptor? Another computational analysis was performed, and we managed to understand that in case of all the platinum complexes that we were discussing, that platinum behaves like a weak nucleophile and in the interaction, and that makes this contact slightly polar. And in the case of the palladium complex, the electrophilic nucleophilic roles were undefined, and that makes this contact nonpolar. Another important question, well, I like questions, can metal-involved interactions be strong enough to influence the structure significantly? And the answer is yes. In case of the three-dimensional potassium iodide structure, we have managed to cut out a one-dimensional polymer of potassium iodide using the organic beam-based ligand. And it is really interesting structure from the crystal engineering point of view. So we were again trying to study it using some computational techniques to understand, does actually the nature of potassium iodide interaction change during this contact, during this structural organization or not? And the answer was, no, it remains essentially the same. However, in this potassium nitrogen interaction within the structure, it was the strongest in the system. So it made us assume that it is the driving force for the structural arrangement. So summary, or years of my work in 2 minutes. Non-covalent interactions represent a useful tool to create polymeric compounds with different 0 to 3-dimensional geometries. The choice of appropriate donor-acceptor pairing influences the strength of non-covalent interaction. For studied systems, it increases for halogen bond donors in a row iodoform, fluorodobenzene, diiodine. And although the dimensionality of the system is closely related to the strongest non-covalent interaction, in our case, halogen bonding, the weaker interactions, such as metal-involved interaction, hydrogen bonding, pi stacking, play an important role in supplementary stabilization. And metal-involved interactions not only additionally stabilize the structure, but also they can play a crucial role in the structural organization. So for example, this potassium-nitrogen interaction is the driving force for the structural organization of the one-dimensional potassium iodide polymeric structure. So now, two acknowledgements, two important things. I would like, of course, to thank Professor Matti Hauka, who is not here, but hopefully he's watching now. So he is my scientific father, and I really want to thank him for all the support, wise advice, and cheering me up during all these years of roller coaster in research. Of course, our EMS research squad for all the silent conversation during our group meetings, for kahvi ja pullahetki, for being cheerful and really nice guys, for the staff of the department who really helped me, for all the collaborators, of course, for my favorite atoms in the multiverse, Yevgeny and Evelina, and all of you online and in the auditorium who are listening to me and supporting me today. I'm really, really grateful. И также я хочу сказать спасибо всем моим русским друзьям, родителям, кто смотрит это сейчас. So Now, let's go to the roast of the defense.
Thank you, Margarita. Can you hear me?
Yes, I can.
Good. So I'm going to start with a little opening statement, and looking at your title, I realized that if we had been sitting here 40 years ago, your dissertation would have looked very different. At that stage, non-covalent interactions would have probably meant hydrogen bonds, strong hydrogen bonds, OHO, OHN kind of hydrogen bonds. Of course, supramolecular chemistry at that point hadn't even been, the word hadn't even been coined. We didn't even know what it was. Self-assembly was also not thought of. Chemists, if thought about assembly, they thought about any kind of chemistry. So self-assembly wasn't also a term that we had thought about. Metallopolymers would probably have meant something like a covalently bonded complex. So metal, 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 ligand, metal, something like that. So we have come a long way in the last 40 years. And of course, as you've shown us, the term non-covalent interaction covers a huge range of contacts, including now not just the strong hydrogen bonds, but also weak hydrogen bonds, even ones involving carbon atoms, which of course 40 years ago was not even thought of. Obviously, halogen bonding at that stage had been kind of mooted by odd hustle, but people weren't really sort of focusing on it. So it's good to see how much you are using the concept of halogen bonding in your work. Of course, other related sigma hole type of interactions, pi interactions at that stage also hadn't been thought of very much, and even metallophilic interactions that you mentioned a number of times had not been sort of really thought of until the end of the 1980s. So over the last 20 years, there's obviously been an explosion in the number of studies that have investigated these kind of interactions and how they can be applied in a wide range of fields. And so obviously from these studies and what you've shown us as well is that we can, that we understand to a certain extent, maybe not completely, what the origin is of the interactions. We know, as you showed us, that there's a huge range of strengths and properties, and you've also shown us that they can be manipulated to produce specific outcomes. And of course, this is where the concept of crystal engineering comes in. So 40 years ago, crystallization was done to purify compounds. The idea of bringing two different compounds together was unheard of. So the kind of work that you're doing is really sort of opening up the field to be able to utilize these kind of interactions to produce multi-component crystals with specific properties of behavior. And of course, much of the research in crystal engineering up until now has focused on organic compounds. There's been a lot on organic compounds, and there's been much less attention paid to the metal complexes, particularly with respect to the role of halogen bonding in crystal engineering. So whereas you've shown that, that metal complexes with these halide ligands, as you've had, are very rich sources of interactions, and you've applied a lot of different kinds of interactions to form your different compounds. And it's nice to see how all of those things work together. And of course, what you've also noted is that the complicating factor is the variability of the metal center. That of course, chemistry with carbon is easy. You know, if you've got a carbon, you know exactly how 4 or 3 or 2 molecule, or at least atoms, are going to coordinate to that. But with a metal, there's this distortion that can happen, and this can lead to very interesting things happening, as we saw from you. This coordination, changing coordination sphere around the metal center makes the design of crystal engineering synthons involving those metal centers very complicated, and you've shown us that in your work. So as a result, this kind of study that you've done is very important to help us understand how we can design and manipulate metal complexes to produce crystals with specific properties and behavior. And this is particularly true when unexpected results are obtained. And as Isaac Asimov was reputed to have said, the most exciting phrase to hear in science, the one that heralds new discoveries, is not eureka, but that's funny. And I get the impression from your work that you had that a lot, that there were some interesting things that you saw and you went with them. And I think that that's very good. So if there's nothing else, then I will move over to starting the questions.
Yes.
You ready?
Sorry, just a moment. I think maybe I have to increase the size of this. Yeah. I'm really excited.
Okay.
Let's go.
Let's go. Okay. So one of the first things that you defined in your thesis was crystal engineering. And yes. So on a day like today, do you believe in crystal engineering?
Well, of course, my work was kind of stick to the crystal engineering. So, you know, when you do something that is really close to this topic, I think it's a good idea to believe in it. So especially, well, if we consider pharmaceutical chemistry nowadays, crystal engineering is something in there. So I assume we can say we can believe in crystal engineering, although the term is a little bit tricky, but still sometimes we have to be like really wide in our definitions to fit things into the definition.
I agree completely. So to take that a step further, you were talking a lot in your presentation about dimensionality control. How controlled was the control, or was it maybe not so controlled?
Well, I think the easiest kind of a control was done with the simplest molecules. So in this case, for this very hindered platinum cyclooctadiene complexes and the simple iodine molecule, then we kind of can control and can expect something like in advance before the experiments. But already when we go into the iodoform or this fluoriodobenzene, there's so many interactions that can be involved, and they can all play important role. Even slight role matters in this case. So and then it makes the prediction quite complicated. But I think that works like mine in this case, they kind of give a hint what can happen. And the more data we have on these interactions and these systems, the more we can try to statistically analyze what will happen further.
Yes, no, absolutely, because there are many variables, and so trying to limit the variables and understand which ones you can manipulate and which ones you control is very important. So to follow on from this, as scientists, we are in general very successful people. We're used to, from school, we work hard and we do well and so on. We don't like to admit failure, but in crystal engineering, I think that failure to produce an expected result is as much a learning opportunity as getting what we expected. I know that you did report some unexpected results, like for instance, those potassium iodide results, but did you get any failures that you didn't report and that you think that it would be helpful for us to learn from?
I'm a PhD student. Of course, I did have plenty of failures. Starting from when you begin after your master's degree, you don't have much skills. So you try, and of course you fail from time to time with some stuff. But if I'm talking about some experimental details that I've got in the end, the really interesting part for me was exactly this potassium iodide structure. That was actually my first publication, so my favorite baby from that point of view. Evelyn, I'm sorry. But in that case, we were actually trying to synthesize real metallopolymers. So as you were saying, the one that are covalently bounded, usually those are considered like a real metallopolymer. So in that case, the synthesis didn't go according to the plan, and the ligand did coordinate instead of the potassium iodide to this, instead of the platinum complex, it did coordinate to potassium iodide, which was, as you say, oh, wow, surprising. and it's not a eureka, but it gave some nice insight. So, okay, this can happen, and these interactions can be more favorable than the ones, the classicals that we would be expecting. And of course, there are some other things that I have performed that are not included in the thesis, not because they're a failure, but just because I didn't have time to write all the papers in the Word. But yeah, I did get a lot of failure, and this failure really taught me to try a little bit more all the time, starting from sometimes that experiment doesn't work, so maybe you need to use the computational chemistry, and I wouldn't use computational chemistry otherwise, so this was a nice motivation for me. Yeah, so from that point of view, that was a really nice outcome. I hope I did answer your question.
Yeah, absolutely. So to continue on with the metallopolymers, you on page 12 of your thesis, you state that molecules are the main building blocks in the crystal that can be assembled into organized structures. And yet, of course, as you said, your aim was to make metallopolymers. Yes. So within the molecules and the metallopolymers, can you explain your definition a little bit more in the context of your study?
The definition of what? I'm sorry.
That molecules are the main building blocks in the crystal, and those are the ones that can be organized into structures.
Yes, of course. So I will try to make it a little bit colorful also for people who are watching it from online and parents. So how I imagine that, like a real little allegory, if you imagine Lego blocks, so those have this little like pimples and then like little holes. So you can build up like really interesting things using different details, like wider or smaller, and you know how moreover it will end up. Of course, if you're a child, you can end up with some really weird stuff happening in there. But if you're trying to organize it in a certain way and you understand the building block quite well, then you can arrange it as a nice building block, exactly as I was trying to say in here. So yeah, that's my understanding of molecule as a building blocks.
Okay.
So I mean like sigma holes and everything like that. So you can try to.
Yeah. We'll get to all of that. We'll get to all of that. Okay. All right. So continuing with the idea of whether we can engineer crystals on the basis of what you were talking about. On page 12, you also mentioned 2 design strategies.
Yes.
So which of these was the one that you used in your work? So maybe just explain to us, to the people who might not have read it, what the 2 design strategies were, and talk about which one you chose for your project.
Okay.
And you do that, and then I'll ask a follow-up question.
Yeah. Okay. Yeah, that's actually a very interesting question. So starting from the simple to complicated, this is exactly like, okay, sorry, 2 strategies. One from simple to complicated, and the other is a retrospective. Well, retro means something from the basis, let's say so. So in the first, from simple to complicated, you first think about your molecules, and then you try to assemble them, like trying to predict how they will interact, and then you perform the experiment and hope that it will work the way you were thinking if you have enough data and experience. And in case of the synthetic strategy, you first try to imagine what you would like to have. Then you try to split up the bigger picture, let's say, to smaller parts, and then out of the smaller parts you choose your starting materials, and then you have the procedure for that. So and I was choosing the first one, from simple to complicated, basically because it was simpler in my idea, and a lot of the metallopolymers that we were trying to do, we didn't really know how it will end up like that well, because it was never done with this molecule. So there was not that much data on that. There is some, but again, like chemistry is a very precise science. So even if there is something similar, it doesn't mean it will go the same direction. And that's why that was simpler for me.
Fair enough. So can you give us advice on, if you were to start, if somebody else were to come to you and they say, I have this project, which design strategy should I use? What would you do? What would you advise somebody? When would they use which strategy?
Well, it depends on the motivation. If you want to create some material, so you already have a plan of this material in your head. So then I think the retrosynthetic strategy would work. But if you are a PhD student who needs fastly to publish some results, then probably you just want to use the first one and then just try to see what will happen. Because, well, sometimes clever strategies, like the retrosynthetic strategy is a very wise, like clever strategy. But the problem is that if you are limited with the time, you might not want to use it, or if you're just like the one researcher on this field. If there are several, like big group is working, so why not? Then you can have somebody does this, somebody does that, and then you can have a big paper coming out. So yeah, and we are really interested about the papers as well, just because you want to spread this knowledge afterwards, let's say so. Yeah.
Fair enough. Yes, I think that this is the idea is that with our science is that we're at the moment in the gathering stage, which is design strategy 1, but that at some point we need to be able to move to design strategy 2.
I totally agree.
And I think that probably within organic compounds using halogen bonding, I think we're much closer to being able to follow design strategy 2. But I think that in terms of metals, because there is this variability, I think it's much more difficult to use design strategy 2 at this stage. So hopefully your kind of work will be able to allow future scientists to be able to follow that. So
I hope so.
Right. Good. I noticed in your presentation and on page 15, you have the statement, simply if an interaction has physical consequences, it does exist. I like this. This is a very nice statement. It's a very nice, neat way of putting it. But I would like you to expand a bit more on what those physical consequences are. That if the interaction has that it will, how can we know that it exists?
So for example, if we do some co-crystallizations and we have some halogen bonding within this system, and one of the starting materials would be like, for example, liquid, and the other would be the solid material. But then in the end, you get something new from something old, and this would be a solid material. So from that point of view, this is something that has physical consequences. Or from the other point of view, it can also influence some physical properties like melting points, like luminescence, for example. So something physical that you can really register, for example. Yeah.
So something you can measure.
Yeah.
Okay, fair enough.
Well, yeah. That would be really fantastic if we can do it all the time.
Yes, it would be. On page 18, you showed a figure. You actually also had it in your presentation. Yes. I think it was slide 5 or 6, which shows the different kinds of interactions involving metals. So you've got some polar ones and you've got some non-polar ones. And I was interested in the polar metallophilic interactions.
Yes.
Can you give me some examples of those?
Well, not really precise because I don't remember the molecules itself, but when I was reading the papers, they were really interesting metallophilic interactions when there were like heterometallic interactions. So for example, like mercury with platinum, like gold with copper. So in this case, and in those studies, what I saw, and they were actually doing some computational chemistry, so they were trying to see where the electron density shifted. And well, this is what I call polar non-polar. So like non-polar is when it's like more or less even and nobody's pushing, nobody's pulling. So everybody's equal. We have a communism. But in case of, sorry, I'm Russian, so I have to mention communism. And in case of non-polar metallophilic interaction, that's exactly the case when nobody's pulling, nobody's pushing, everything is equal, everything is fine. So yeah, that's what I meant, at least.
Yes. So I was wondering whether this could have been utilized in your study as well. Do you think, is this the kind of thing where you could have had mixed metals, palladium and platinum, that you could have had some kind of chain? So because you had those chains of platinum, iodine, platinum, and palladium, iodine, palladium, could you have replaced one of those with something, with another metal?
Well, in my case, most of the, well, at least in the complexes that are represented in the thesis, we didn't have like really like this metal interaction. It was more like metal iodine interaction. So that's a little different story. But if you're talking about if we can just have various complexes interlinked via halogen bonding, for example, and probably there will be something. So I guess this is possible to try to design it like this, but I didn't try. So
yeah, okay. No, I was just wondering whether it would be possible, because I was thinking maybe if, because you found that the palladium and platinum interactions with the iodine were fairly similar, but if you had something where there was a slightly different interaction, that maybe you could have had a different metal, and then an iodine, and then a metal, or something like it might. You could have had some. There could be some quite interesting things happening there.
Well, for the square platinum complexes, I think. Oh, sorry, not square, just square transitional metal square complexes. I think it's possible to create this kind of a systems and try to also involve the halogen bonding. But I'm not really sure which one would be then stronger, because halogen bonding seems to be dominating in this systems. So even the ones that I was representing, this metal, I didn't actually call this metallophilic interaction. I called it metal involved, just to be safe, because well, there is this iodine and the platinum. Of course, there's interesting how they're interacting, the nature and stuff. But again, that's why I didn't really want to bring the metallophilicity into that area.
Fair enough. No, I think that's a sensible way of doing it. So to moving on to the non-polar interactions, and you talk about the intermediate metal halogen interactions.
Yes.
Can you talk a little bit more about those?
Yes, actually, that is, I think my paper number 2 was really focusing on that. And that arises from a collaboration. I went for 1 month to my St. Petersburg colleagues to St. Petersburg. And actually in there, they have mentioned already, they managed to achieve some of the intermediate metal halogen interaction. They had some nickel complexes. So this is from Kukushkin's group. And there is this one guy, Daniil Ivanov, really wise and really nice guy. So they were doing together and this intermediate metal halogen interactions. So in this nickel complexes, it is really tricky to see whether the interaction happens via the electron belt or the sigma hole. So they had to perform some additional studies, and they still, because the nature was unclear, that's why they call this intermediate metal halogen interaction. And I was doing kind of a continuation of this work. So with this platinum palladium isocyanate complexes, as I was showing on the slides, and what we found was really kind of, there were some similarities between our complexes, well, logically nickel, platinum, palladium, and their complex. So then it felt within this range, and it was really nice to see that something like that happened. So yeah, that's a unique structure, but structures that we got, but still it's something that was already there.
So, and you described that as a non-polar interaction, because I was wondering whether it could be that the positive area interacts with a negative area on the metal, and the negative area interacts with a positive area on the metal complex, and whether it's non-polar is really the correct way of describing it.
And that's why we did this kind of a computational analysis. So this electrostatic potential versus the electron density. That's just something, as far as I remember, the Espinosa was the first to perform it. And they were just trying to see where the electron density is going through so is it like in between those two, like in the classical covalent bond concept when they're sharing, or is it attracted more to one or another? And they saw that there is not much of the they also saw that it is like a shared interaction, and that's why it's kind of non-polar. Yes, it's a kind of a new term. If you mean that's a little bit tricky, but this is what was meant.
Yes, I'm not sure non-polar, but maybe just not polar, which is, I don't know whether there's a difference, but in my mind there is.
Okay, so. Yeah, but I'm not a native speaker, so that might be the case. Maybe not is a little bit better, but again,
I don't know. Yeah. So continuing on from this, if you were to take on a new project, so I assume that you're going to go and do something else, and you wanted to do crystal engineering with a metal complex, which of these metal-involved interactions would you use if you wanted to use some kind of crystal engineering synthon to go and produce new compounds? The one that you believe would be the most important in guiding the formation of new crystals?
Well, most important is a little bit tricky. I mean, there are a lot of complexes that are important, and usually we're trying to consider if they have further application.
Sure, no, but let's say you're looking at a specific kind of complex, and you wanted to design some kind of crystal that has some property, and but you needed to engineer the crystal to have a specific, now that I'm formulating my question, it doesn't make any sense anymore.
Yeah, I'm a little bit lost.
Okay, forget that. Let's move on. I need to think of a better example.
I have like a little answer on that. As far as I understood the question, well, actually, I was really thinking to try maybe one day the nickel version of the complex, like the same of this isocyanide. It was actually even there's synthetic procedure how to synthesize this nickel complexes, and then we can probably even further throw it into the this halogen bonding and see what will happen. And the problem was that I was a little bit too pregnant to perform this experiment, so I had to stop on the platinum palladium, if I'll be honest. But another thing that I would probably try to do, keeping the same complexes, but trying to play around maybe another halogen bond donors and seeing what will happen afterwards. That would be also really interesting to check. But those that I had already, I think they're also giving some nice insights on this weird interactions.
Absolutely. Good. Okay. So on the next page, on page 19, I think it's near the bottom, you say, due to the difference in DZ squared nucleophilicity of the platinum 2 center compared to the palladium 2 center, it is possible to turn the Mi interaction on or off. Please, can you clarify that statement? What do you mean by that?
That's maybe a little unclear statement. Actually, now I realized that, but I was trying to be really generous writing this. So what I meant in here, that's actually meaning my own paper as well, because it was just written, so it was still fresh in my head, and that's why it is like this. In case of the platinum centers, we have the metallophilic interactions, while I think in case of palladium, we have metallophilic interactions, while in case of platinum, we don't. Sorry, just give me a moment. My pregnant.
I think it was the other way around. I think you were right the first time.
Yeah. Sorry, my pregnant brain is like giving me tricks. Yeah.
Is that what you were referring?
Basically, one metal has the interaction, the other kind of, if we simplify the model, so I can try to explain, and if the other doesn't, so like those are different complexes. Of course, we are not switching. We don't do some kind of a synthesis while we're changing the metal center straight away. So the switch, what I meant is like we just have the two different complexes, and if we want to have this interaction, we use one complex. If we don't, we use the other one. So basically, that's what I meant.
Okay, so my follow-up question was, how could you utilize this in crystal engineering? And then, which you've actually already answered that. So
okay, good.
That's good. All right, moving on, page 2. Is your statement on page 21? You make a statement: a shorter contact means a stronger non-covalent interaction. Is that always true?
Not always. Well, no. Yeah, but okay. If we consider like in a lot of cases when we have like a classical halogen bond, it's like getting shorter than in non-halogen bonding interaction, let's say so. But in many cases, this is an indicator, and to my mind, actually, like this is why we have to use a combination of like either experimental methods to confirm that it is stronger, or also a combination experimental and theoretical methods, and then we can say more surely, not for 100% sure. As scientists, we're never sure in anything. We doubt things, and this is how we do the science. So yeah, this is how it's done. But yeah,
I agree completely. I agree completely. It's you need to have proof. If you're going to say it's stronger, then you need to actually have proof of it. You can't just saying that it's a shorter distance doesn't necessarily make it so.
A combination is always a better
combination
option.
is always important. Absolutely.
Yeah.
Okay, and then we come to the fact that you use Bondi radii for your study, even though they were determined nearly 60 years ago, and there are many more recent studies. And I admit I do the same. So it's not judging you in the least at all. But I think it's a conversation that we actually should be having more often. And I would like to hear your reason as to why you chose to use those.
Well, I think it's kind of the same reason that in some cases people are using the same like basis sets or functionals, just because there's more data on that, and then you can compare with some other papers that are doing the same work. Another reason for the Bondi's van der Waals variety, it's quite short. Like there are some other van der Waals variety that, as you were saying, they're updated and maybe more precise in some cases, but they're like wider. And in that case, sometimes you can probably get more interactions, and it's cool. But in case if you're using Bondi, that maybe we're a little bit more like strict. And if it's with the Bondi, then probably it exists. So yeah, that's the whole point. So first of all, the referencing. The second is like, it's short enough. So size matters in this case.
Very good. Good. Okay. All right. Moving on to section 2.2. Here you introduce several theoretical methods.
Oh, yes, I did.
So there are lots of different methods. I'm not going to ask you to go into the details you've done. You've explained very nicely in the thesis.
Yes.
But now if you were to undertake a new project involving crystal engineering, and you were told you have a limit to which of the theoretical methods you could use, which one would you consider most important for your study, and why?
This is like with the babies. Sometimes you do something and you get attached to this method. Although it might not be like the most modern and most best and so on. Actually, when I started to do this computational chemistry, I was always like thinking, what is the best method? What is the best functional? What is like everything has to be the best. So like everything will be according to the plan. And then I just smashed into the wall that some parts are not working together. And you have to choose as just you say. But what I really like out of this computational techniques, if I say, I would definitely leave, well, NCA plots is kind of nice method, but now there is also this Dory which came, which is even more modern, like, but I kind of like it because it gives you this estimation of the strengths, and it's just like a relative strengths comparing to Qtame, which sometimes misses some of the interactions, and it's a little bit well, it's not outdated, it still works, it's still great methods, but I kind of personally prefer the NCA. I would leave it for sure. Out of the next methods, I kind of really like this ED, ESP minima profiles. Those are not quite wildly used yet. Probably this will improve with time, but this is a nice idea of this nucleophilic, electrophilic nature. I kind of like it. And I like this kind of a considerations, who is who. Yeah, that's what I really keep. Electrostatic potential surface. Well, I don't know how needed is that and how much like extra information we can extract out of it. It is still a nice method, but if I have to choose like the limited amount, I think probably I would omit that that one. So I would leave the NCI plot, this ED, ESP studies. They're really nice. ELF also gives some nice pictures. I really like the pictures. They're so bright.
Yes, they do give very nice pictures, I have to admit. Yes. Good. Okay, thank you.
Welcome.
So one of the terms that you use quite a lot throughout the dissertation is philicity, which obviously could be a general term for things like hydrophilicity, but you're obviously not using it in that context. Please, could you define what you mean by philicity? And I have a follow-up question, but I'll let you answer that first, and then I'll get back to it.
I assume it comes somewhere from Greek or Latin.
I would guess so,
something
yes.
that feels something, or like this philicity, it means it wants something. So nuclear philicity, it's something that wants a nucleus or something that is positively charged. Electrophilicity is electron lover, let's say. So it wants some negative charge to itself. Metallophilicity. That's a little bit more tricky concept already.
Well, but you were mainly using it in terms of the concept of nucleophilicity versus electrophilicity, right?
Yes, that was my main use of this philicity concept. Yeah, exactly.
And so how would you use those principles of the nucleophilicity, electrophilicity in terms of crystal engineering rather than just like synthons?
Well, here comes the electrostatic potential into the game. And my favorite Lego example. So you really want to stick things together. And in this case, when you have some kind of a nucleophilic or electrophilic region on your molecule, you can try to put something according to it. So if it has this nucleophilic region, you want to put something electrophilic into it. So basically you stick them together. And this is how you plan your experiments. Maybe from that point of view, I shouldn't omit the electrostatic potential surface analysis. Because it gives this nice hints, and I really imagine it as a Lego blocks describer for this molecules.
Yes, yeah. No, it does. It describes it very well. Yeah. Okay, right. I think I have covered all my questions with regards to the methods. So let's move on to chapter 3. Okay. Which is where you introduce the compounds that you used in your study on page 31. Why did you decide to use iodoform rather than something like tetrafluoroiodomethane?
That's an interesting question. So first of all, it was really available for us. And this is a really interesting molecule from my point of view. This is a solid compound, nice halogen bond donor, and also it has the possibility of hydrogen bonding. So from that point of view, this molecule seems to be really interesting, and it's really well, it's easy to work with that. There are some limitations, like trying to work in the dark rooms, and a lot of my colleagues, they were really scared when they were coming to the diffractometer room, and I'm there like all in the darkness, just like a little bit of a light to choose the right crystal, and then like, don't turn the light. Yeah, but to my mind, this molecule gives really nice possibilities and many sites for the interactions, different non-covalent interactions possible. So from that point of view, that's a really nice one. Why not?
Absolutely. So it was difficult to tell from the paper, but it seemed that each iodoform was involved in a hydrogen bond, but only one halogen bond. Is that correct, or is it just, did I not get it properly from the picture?
How did it happen? Did I have this? No, I don't have the slides. But I think if I will just try to see it in the paper, I think I have a nice representation. Yeah. So if you go to the probably you don't have it. Is it published? Yeah, this one is published. So the crystal growth and design paper. And in there on the, what page is that? Page B? Is it page B? Results and discussion part. So there is actually a nice crystallographic structure that is explaining it. So iodoforms were actually all the iodines were involved in halogen bonding, but
oh, okay, I see now. Figure, yeah, okay, yes, no, I see it. I beg your pardon, I missed that one.
What wasn't involved is actually the second iodine from the platinum complex. So only one iodine was involved in the non-covalent interaction. The second was a little bit too hindered, so well, to my mind, and that's why it wasn't involved. So yep.
Okay. So that then gives it a sort of a nice sort of two-dimensional sort of almost ladder.
Yes, true.
Okay, nice. No, that's a nice
Yeah,
structure.
the structures are so nice to rotate around. Like this is what I really like to do.
Yes.
After you get them, you just rotate them. Yeah.
And you only seem to have got one compound with the iodoform.
Yep.
So this is again one of the things that failed, I gather, is getting the others.
I think I even wrote about that. So we didn't manage to. I don't hide this kind of things. So we just didn't get the co-crystal. So it was just the starting material for the bromide and chloride version of the complex.
Do you have any idea why?
Not much, actually. I would like to know what.
Yes. Chemistry. Chemistry happens.
I mean, that would be logical if this would happen. I mean, still the iodoform has the needed sigma holes. There's hydrogen that has this positive potential, and the chloride and bromide, they're supposed to work. I mean, they have this negative potential on them if we do this ESP analysis in advance. So in advance, it was looking like it should work. In the reality, chemistry happened, as you say.
Exactly.
Yeah.
So that paper is nice, and one of the things that you also mentioned in your presentation is that the iodine and the I'm just going to call it Fib as well, have similar sigma holes, but you, as you pointed out, the iodine ended up having stronger non-covalent interactions.
Yes.
Why do you think that is?
That's a very, very good question to my mind, because like it would be expected actually that they would be rather similar. But if even we would go and look in the numbers are still quite similar. So I mean, it is medium, like in that presentation, and comparing to the iodine complexes, but it is medium, but very close to the iodine. So it's not as drastic change, let's say. So they're not that different in strengths with the iodophluorobenzene and the diiodine molecule. But if I have to like give some idea why this could be stronger than the other one, I don't, well, the guess, maybe just pointing into the sky, maybe the iodine has a little bit better polarizability, and just geometrically it goes a little bit better to this interactions. Fib is big guy, well, bigger than the iodine molecule, and as well it also has some additional interactions that can be involved, and maybe just because it is involved in something else, so like especially the pi stacking. So the halogen bonding in this case is not getting as dominant, and iodine molecule doesn't have much else, let's say. So it goes for halogen bonding. So it's just straight away, and that can use its force as full. So that would be my
Yes.
Yeah,
or it could be that there are repulsive interactions between the Fib and other things that end up weakening that interaction. That makes sense to me.
True. Yeah.
Okay, so we've spoken about the halogen bond donors, and you sort of vaguely touch on the design principles. So we're still on page 31 here, that were involved with choosing the metal complexes. But I'd like you to go into more detail as to why you chose those particular ones that the metal complexes that you used.
The original metal, not the halogen bond donors, but the metal complexes.
Metal complexes.
Well, yeah, why not? It's a great question. I really like to answer to that. So platinum palladium cyclooctadiene isocyanide complexes, sorry. Those are square planar complexes, and they have this available z square orbital, which we can try to play around and see what will happen. More out of the curiosity, so they're really available. And if we consider the cyclooctadiene complexes, they're a little bit more hindered. So from that point of view, we can try to avoid the metal involving interactions, although as you saw already for the iodide complex, it didn't work. So there was still this metal involved interactions, although it was weaker than for the platinum and palladium isocyanide complexes. So basically that was the whole idea. And those complexes as well are quite simple to work with. So they're not that super dangerous, let's say. So, well, making them, well, because I also did the synthetic part for this work. It's not just like I took the jars and mix this up, although it happens a lot with the co-crystallizations, but making them was a little bit more challenging because the cyclooctadiene is quite hazardous, and the isocyanides are also not the best healthiest compounds to work with. But when you made already the complex, it is very simple to work with, and it just goes straight away. And as a PhD student, of course, I want to have some results really fast. So then I can study these molecules as soon as possible and as deep as I can.
Okay, good. All right, so let's move on to the results of your project, and let's talk first about the metallopolymers that you made and focus on the dimensionality of the different systems. So you spoke about that in your presentation as well. Let's start talking about the platinum halide cyclooctadiene complex. So what do you think is special about the chloride complex that allows it to form the one-dimensional chains, as opposed to that's with the I2, as opposed to the zero-dimensional heterodimers that you got with the bromine and the bromide and the iodide analogs?
Yes, that's a very good question. And well, I don't have here this beautiful picture of the electrostatic potentials, which I did perform for all of these molecules. I think it's an essay for this article. But the thing is, if we consider iodine and bromide versions of the complexes, and if we just model the electrostatic potential for those, there is this anisotropy on the halide atom, and this anisotropy is actually on the kind of a bottom of this complex. So like it goes like in the actual position of this bromide and iodide, while in case of the chloride, actually the whole anion, if we calculate it, it was all there was not much of the positive electrostatic potential on it, and so there was not much of anisotropy on it, and therefore I think the iodine can be more flexible to coordinate wherever it wants to, while in case of the bromide and iodide versions, it was already limited by this anisotropy on the halide of the complex.
So do you think then that if you were to slightly change your iodide and your bromide to, well, I don't know whether you could reduce that anisotropy, but whether if you could, would you be able to get one-dimensional chains with iodide? Let's say you had a different ligand, not the cod, but something else.
So some ligand that will influence the anisotropy on the iodide and bromide interaction. Theoretically, I would say yes. If we have a certain electron, in this case, electron donating group, like if it's quite strong enough to push quite a lot of electron density towards these guys and make them as how do I say, as even in the electrostatic potential as possible. So yes, probably there will be this possibility to create the 1D dimensional chain. Although I think it would be easier to make the chloride version of the complex heterotrimeric.
Yes, you're probably right. Yeah. So in terms of so thinking back to the topological design approach to crystal engineering, yes, then this would probably, I think I agree with you that this would not be a successful way to make one-dimensional polymers. It would be easier to make zero-dimensional chains. Okay, it's good to know.
Yes.
Yes.
I think so. Again, we have chemistry behind that, so it can play all games, but
exactly, yeah,
that's what I would be assuming.
Okay, good. All right. So, but one of the things that I found interesting about this paper, so this is paper 1 describing this work, was something that I don't think you actually mentioned in the dissertation, but it came out very clearly for me in the paper, and this is the changing of the iodine bond lengths. So you mentioned that the II distance of the iodine when halogen bonding with a chloride complex is longer. I've written longer. It's actually should be shorter than the crystals of the pure iodine.
Yes.
which of course is and you point that out in your paper as well, is unexpected.
Yes.
Do you have any ideas to why this is happening?
Not really. No, that was really like I was surprised myself when I was writing down this. Like you would really expect it to be not shorter but longer, because when halogen bonding is happening, this what is it called? Molecular iodine, or the molecule that is involved in like halogen bond donor, usually has the extension of the bond itself, like covalent bond that it has in it. But in this case, it didn't happen. And I was really surprised myself. So like nothing came to mind like straight away to my mind. Why can this happen? So I can't really elaborate.
Yeah, because typically what happens is it's electron donation into that anti-bonding orbital.
Yes. So it's supposed to make it longer.
Yeah,
and
exactly.
That's why it doesn't make much sense.
Yes,
but
you know, this has been observed before. Pavel Hopsa has done some calculations on what he calls blue shifted halogen bonds. I don't think he's particularly looked at iodine, but I think he's looked at organics involving iodine. And now that I start to think about it, I actually can't remember what the origin of that blue shifting was. But
so I will try to check it out. That's really interesting. Yeah, if somebody pop up into the same problem, let's say so. So
yeah,
that's an interesting challenge in here. Yeah.
Yes, I mean it could also be a very interesting design principle, is to have these shorter interactions or shorter bond lengths with the interactions. You could fit it into different sort of shapes, and I don't know, it could be quite interesting. Okay, so in figure 22 on page 46, which I can't remember whether you showed in your presentation. I think you might have done.
I've omitted that, although like I really like this picture. It was also this ELF projections was done by Daniel Ivanov from St. Petersburg. Really beautiful. When he showed me this picture, so I was like, oh my god, this is so cute.
It's lovely. It's a really nice picture. Yeah. So you show there that iodine metal bond path that passes through the filled dz squared orbital.
Yep.
And that made me wonder about the directionality of these interactions, because if you look at those dz squared orbitals, they look quite localized. So, and obviously, I mean, you say that interaction is weak, which it would be because it's obviously the iodine is the strongest interaction.
Yes.
So that's the one that's kind
between these two. Yes. So that's why it can be like using the full power of the dz square orbital, let's say so.
Yes. So that was what I was wondering, is if you didn't have that, sorry, move my finger up. If you didn't have that halide, whether you could have that, or if you had a different halogen bond donor, whether moving that iodine would result in a stronger interaction if you were to get a much more direct kind of overlap with if the dz squared orbital is here, and then your the halogen is kind of pointing directly at the dz squared orbital, whether that would have a greater influence on the packing, if one could do that.
Well, that's really, you mean like if there won't be this halides like iodine in case of the complex, there will be some other ligand. I'm not sure how the iodine will then pack, and what is the driving force for this interaction? This is actually really nicely questionable. Big question for this compounds, whether this iodine interaction is the main force, and then the platinum is more like a coincidence, let's say so. So if we will remove this ligand, we might know then maybe more surely, and then we can be like we can say more precisely that yes, this metal involved, not metallophilic, metal involved interaction is really strong enough to exist in this case. It's a little bit more tricky to for sure say, yes, if we change the halide to something else, then the iodide will just fill this as a square orbital and they will just interact with platinum and this interaction will be stronger. I can't really say. And again, we have to consider the really strong influence of the ligand itself on the complex. So there is a really complicated situation. So that's why it's really tricky to answer this question like with 100% sure. Like I can't really say anything, being a scientist again.
Yeah. No, I agree. I think it's something that one can consider and think about. Yeah. So let's talk a little bit more about these iodine platinum and iodine palladium non-covalent interactions. You call them quasi-metallophilic. So it's known that gold has halogen-like behavior in several complexes. You see that written fairly commonly.
Yes.
So do you think that this means that we can take it the other way and say that iodine can have metal-like behavior?
I think so. I was just recently talking with my husband when I was preparing for this defense. He sent me a really funny paper that should we consider halogen bonds as also the pi involving interactions, because they're really kind of remind. There was one really nice paper. I don't remember the surnames of the authors, sadly. My really bad memory now doesn't help me. But the thing is that they tried to explain this halogen bonding very similar to the what is it called? Pi bectonation in the metal complexes. So from that point of view, it's kind of similar. Well, this was one paper, of course, so it was quite fresh, 2020. So if I can remember this knowledge and talking to you, so I would say, yes, we can really try to consider that iodide maybe have like this metal-like, well, it's not, of course, it's not a metal, but like quasi, if we will call it like that.
Yeah, okay. And under what circumstances do you think it would be true that we could have an iodine that would have metal-like behavior? What do you think could I mean, what is it about your complexes that lead to it having this kind of sort of, you called it quasi-metallophilic behavior?
So why do we call it palladium-metallophilic behavior? Well, it depends on as I really like this concept, who is nucleophile, who is electrophile, so who is pushing, so who is pulling. And in this case, we want to see how the iodine works. So in case of, well, palladium, we can't really say anything because it was a non-polar interaction. But in case of the platinum, we really saw that it has this nucleophilic. So iodine was working as an electrophilic element in this case. But again, this was more similar to the halogen bonding. So this is a little bit tricky to directly reply. How do we call it?
Yeah, it's difficult to kind of sort of differentiate between the behavior of the metal and behavior of the iodine. So yeah, okay, I understand.
Yeah.
Okay. Good. So let's move on to the polymeric potassium iodide compound.
Yes.
So you mentioned that the ligand bite angle may be crucial for producing the one-dimensional chain on the cubic K4I4 units. Can this lead you to suggest any similar modifiers that you think should be investigated?
Actually, well, when this paper came out, we were really, not paper, when we got this really interesting structure, we were really interested exactly in the same question. Can we really have some other ligand, maybe like with a slight difference that will have the same impact? So what we tried, I think I have it on the paper, but I'm not sure.
There is one that you tried in the paper, yeah.
Yeah. So we tried a little bit different ligands with the nitrogen on the meta position, and actually it didn't work. And like actually I tried like several different ligands, but it seemed like this one was exactly we would call it selective. We won't say like it's impossible to have with some other, but this one was really selective towards the potassium iodide, and we couldn't have something else. Of course, I didn't try all the ligands in the universe yet, but I have tried plenty, and it looked like this one is working. What would be really nice to try, and that time I wasn't aware much about the computational chemistry, so the QTM analysis that is performed in this paper was performed by a collaborator, and it was my first paper and first actually experience with computational chemistry. So when I get all the data from the chemist, I was scared and I didn't understand what is happening in there. But if I would be now redoing this job, like, you know, like some people are redoing the makeup from the old years, I would be really trying to maybe modify and have some computational analysis, some trying some extra modeling and trying to see which ligand probably will be the most successful, which version will be most successful, and then trying to synthesize it and then trying to cut out a one-dimensional structure of potassium iodide. I have checked like a lot of structures in the Cambridge structural database for the same kind of arrangement, but only our one was this one-dimensional chain. So we were lucky with that. And other ones, they have some units. So for example, like a cubic unit, but then it breaks, so it's not becoming a polymeric one, or like some chain, but it's also really distorted from the original potassium iodide structure. So my answer would be, I think this one is pretty selective, but I think computational chemistry and some computer modeling would give us better idea what we should try, because blindly trying changing the positions of atom doesn't help. I did it. So
yes, yeah. I mean, you talk about the bite angle, but is it the bite angle, or is it actually that sort of nitrogen distance? I mean, maybe if you had something that is it, how flexible is that is that compound in terms of how far can it bend? Just trying to have a look at it.
I think it was well, I don't remember the angles right now, but I think it was flexible, but not too flexible, as there was also additional like hydrogen bonding. This pyrimidazole rings in there. They were a little bit like not glued. What is the word? Like stick together. So like there is this weak hydrogen bonding that doesn't allow it to go too crazy about the biting angle, and this may be the reason. But additionally, as I was saying, there is also some weak pi stacking, weak this, weak that, and that I guess the combination of all of this weak interactions, although they are weak, this gives this unique structure. So from that point of view, it's really interesting that we have something really strong that probably starts the whole structural building, but then the other things they're limiting it towards this one-dimensional chain. So that's a very, very lucky coincidence that we got this one. But that is a very, very interesting structure, and it gives the hint that we can do that. We can cut out this one-dimensional chains. So it is possible for future generations of scientists to try to perform something like that for the ones who will not be that pregnant.
Absolutely. No, I mean, it's a very interesting structure. I find it fascinating. Oh, yes, there was one sentence on the last sentence on page 48, which I didn't quite follow. A strong interaction between potassium iodide and the ligand leads to a sum of the van der Waals rate distances much shorter than the NK interaction. Should that be longer than the NK interaction?
Sorry, which
Sorry, page 48. Last sentence, it says a strong interaction between potassium iodide. Can you just explain that sentence? Because I didn't understand it.
Yeah, well, as I was working quite a lot with the non-covalent interactions, like this one, and usually non-covalent interactions are like on the border of van der Waals already, or like a little bit shorter, yes. And in this case, what kind of surprised me that this was much shorter. So actually this was more close to like ionic bond, if we consider like distances, than the like classical non-covalent interactions. So that's what I meant.
Okay, so it's where it says much shorter than that of the NK, I assume that should be much longer. the sum of the van der Waals bond distances is much longer than the NK interaction.
Yes, yes.
Okay, all right. No, that makes sense. Just a typo.
Yeah, sorry.
All right. So you mentioned that those Ki units are distorted, and if I look at table 8 on page 50, I see that the Ki distances are different. So it's not just obviously the distances, it was the angles as well. But I was particularly interested in the fact that the Ki distances were different. Is that related to the ligand orientation, or is that just a general distortion? Were the shorter distances where the nitrogen was bonded to the potassium, or longer distances, or is that not related to where the ligand is actually coordinating?
Okay, the shorter distances, I actually don't remember where were those, but I think actually ligand was bringing them like closer together, so they were becoming like shorter.
Okay.
That was what was happening, and I guess again this is what made this distortion happening. So like there is this strong interaction of the ligand and the geometrical structure of the ligand. To my mind, again, I might be mistaken, but to my mind, this is what made this distortion happening. From the same point of view, what made this compound happening as well. So that is a very interesting combination of happenings that led to the structure.
Okay, that makes sense. So then do you think if you were to do your computational calculations and find a modifier that would be appropriate, do you think it would then be possible to reduce that distortion so that you then have the same kind of little cubes that you get in pure potassium iodide?
So basically, this question means, as far as I understand, would you use the certain ligand that has a certain geometrical properties to create this kind of systems? I really think we should consider, first of all, the ligand's properties, and then, well, in a combination with what we know from the classical ionic salt, if you want to create similar structures. So those are really important to consider, otherwise it will not work. But distortions we have to take in, because we already know that this happens, and when we do the calculations we have to think that yes, there is a certain diapason, range, that's a Russian word, the certain range that we can really utilize. So like in this case, we still get like distortion, but we still keep the structure. So it is still possible to have this distortion within a certain range and get the structure. So if we get the distortion, it doesn't mean that it will not work. So that will be my answer.
Fair enough. So you don't think that the distortion is also to do with the fact that you obviously have a different electronic, the potassium now has a different electronic environment when there's a nitrogen coordinated as opposed to when it's surrounded by iodines. So is it just a physical distortion as a result of the fact that you have this ligand, or do you think the electronic environment may also be playing a role in the distortion?
That's a very good question. I think we always have to consider electronic effects. So if there is an interaction, there is something that is happening. So it's not just like something is glued, and even when we have a weaker interactions, there is influence of this electronic effect. So I would still try to consider those an impact from those, not just the ligands geometry. So I think it's wise to consider those.
Yeah. So presumably the nitrogen was interacted strongly, but if you replace the nitrogen with something else that might also form a strong-ish bond, then that may influence the distortion or reduce the distortion.
I would probably think so, yes. Well, I would think so. But
okay. Interesting.
Not sure, but I would think so. I always consider it's good to consider these interactions, but
Absolutely. Now, this is a bit tricky because I wanted to talk to you about table 9. I don't know whether maybe you could, because I wanted to ask you about to explain to me what's happening there. This is on page 53, but I don't know how easy that is going to be without being able to see it. So I wonder, let me see. I wonder whether I am going to be able to share my screen. If I...
Possible? Sorry.
Let me see if I can share my screen because I've got table 9 prepared. Can you see?
Yes.
Okay. So can you explain to me what were you trying to determine here? And can you explain to me what this told you about the stability of this one-dimensional chain?
Okay. So first of all, then we have to talk about the models that we were trying to apply. And those are represented on the figure 26. So the idea was, it's a little bit tricky to consider the stability of the ionic salt and directly, compare it with the stability of this weird 1D structure that we got. So how can we really see that this is a little bit more stabilizing than the other? Our idea was to create this, well, you can see this lovely cross on the figure 26 made of the potassium iodide. And we kind of tried to, model the same cross that we get from this ligand interacted structure. So from that point of view, we wanted to see how the growth of the structure, so adding like extra unit of the salt and then adding extra unit of this salt plus the ligand increases the structure stabilization. So, and if the increase in the stabilization is higher for the ligand-based structure than for the just salt-based structure, so then the stability, it means that it is, well, not directly, but then it means that maybe it is a little bit better in stabilizing, something like that. This is what we wanted to try, because it's a little bit more tricky otherwise to compare this stabilization energies. And that was the reason for the stable. And that's why we managed to try to see like how, if we just increase the number amounts of these cubes, just 1D structure, then the cross, and then also we compared it to the simple potassium iodide salt. So what was happening? And what we saw exactly that the increase in the interaction energy, so in energy stabilization, let's say, was bigger for the ligand stabilized structure than for this potassium iodide salt. That is the kind of meaning of the stable.
Okay, so that potassium nitrogen that does imply that the high electron density there and the high interaction energy does imply that it is closer to a covalent bond than an interaction.
Yes,
as well. Okay, very interesting.
Yeah, it's a complicated thing that I was actually trying to explain to the computational chemists, like when we wanted to understand how do we compare the structures to each other, how do we compare potassium iodide and the stabilization between the structures. So that was a fun table. my first computational experience ever. So
yes, I can imagine.
Yeah.
Okay, let's talk about cooperative effects. You mentioned cooperative effects a couple of times on page 53 is where I'm looking at. How do you know that the interactions are cooperative and not just simultaneous? Because cooperative means something, cooperative means like with water, that if you have one hydrogen bond between two water molecules, that the energy of that, if you had two hydrogen bonds separately, the sum of those is less than if you had two together. So the cooperativity actually increases the strength of both. It was not clear to me that whether the interactions were cooperative. So in other words, they were not just supporting each other, but they were actually increasing the strength of the interaction.
Yes.
How did you look at that specifically? You would have to do it computationally. I can't see how else you would do that.
Well, out of the computation, we actually, I think we just did, well, at least for the potassium nitrogen, for this potassium, weird potassium iodide structure, there was some introduction energy computations, and that was the conclusions from the computational chemists that those are working as additionally stabilizing interactions. But if I'm talking about my own structures, I think probably then it is not as wise to call them cooperative. It is more like that they're coincident at the same time. Well, maybe they are cooperative, but the computations that I was performing, they're not strong enough to support this idea.
Okay, yeah. Because I mean, they may be cooperative. They may be helping, I mean. So you may have additional stabilization as a result of the fact that you have both. But yeah, I think one must be very careful about using the term cooperative when you actually mean that they're both there and stabilizing the system at the same time. So, but it's something to look at. Yes, now I've dropped my page, so I've lost my last question, which is somewhere on the floor, I think. 2 more questions, sorry. They're gone. Where are they? Hold on a moment.
No worries.
It's gone under my desk. That's why I couldn't find it. Okay. So one of the last statements in your dissertation is it was shown that the dimensionality is closely related to the strongest non-covalent interaction with additional cooperating weaker interactions. So because you had 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional. Can you just clarify that statement that the dimensionality is closely related to the strongest non-covalent interaction? You also mentioned it in your presentation.
What I meant in this case is that this would be narrowing the whole what is the word? Structure building up process. So this is narrating. If there is the strongest interaction in the system, to my mind, that will be something that will influence the most the structural arrangement. Additional interactions are helping, but this is the key concept. So this is basically what I meant. So like the strongest directs from that point of view. It's not like it directs that if you get like halogen bonds with iodine, you will definitely get 0-dimensional structures. This is not what I meant. I meant like this is the narrator.
Yes. Okay. Fair enough. So then just to follow on from that, one of the things that I noticed is that you had 2-dimensional chains, or 0-dimensional groups, and 1-dimensional chains, and 2-dimensional sort of layers and chains and so on of halogen bonds and the metal involved bonds or interactions. And you did get pi stacking that ended up making it a 3-dimensional network, but there was no case where there was a 3-dimensional network that occurred just as a result of the halogen bonds. Do you think, I mean, we're back to the crystal engineering concept right at the beginning in terms of the topological design. So with the experience that you've gained from the study, can you suggest a way that you could generate a 3-dimensional halogen bonded topology that's not dependent on
additional
pi stacking?
Well, first of all, you have to omit pi stacking. It's really tricky to like omit other interactions and like if you want to have so I think there are some really nice three-dimensional structures, not with my complexes, but with some other complexes containing halogen bonding, and especially this iodine molecule containing structures, because they can be I think it's called amphiphilic, if my brain doesn't break me. So it can actually interact in two dimensions, and then you can also have like on your metal complex like two different halogen bond acceptors, so you can play around that and try to create a three-dimensional structure. So something like that I would really try to assume. The iodine version is the simplest one that comes into my mind, but again, this amphiphilicity, I think it's not the unique property of just the iodine molecule. It happens with some other halogen bond donors, so you can play around that. So the vice halogen bond donor, halogen bond acceptor pairing would work, and it is possible to make it.
Yeah, so you would need to have more halogens or more halides on your metal complexes then, presumably.
It's one of the methods, I would say so. There's probably something else that you can try to play around, but that would be the straightaway answer to my mind.
And obviously the same goes for your halogen bond donors as well. So yeah.
The more you have, the
more you have, the more it's going to go ahead. Yes.
The branchy you have.
Wonderful. Well, I had prepared 30 questions. I have asked 30 questions. So thank you very much. With that, I'm going to I've finished my questions, so I'm going to make my my closing statement. So in terms of your presentation and your dissertation on non-covalent interactions as a tool for supramolecular self-assembly of metallopolymers, halogen bonding has received increasing attention over the past 20 years for its potential application in a wide variety of fields. In particular, it is increasingly being applied in crystal engineering to produce novel materials. However, the focus in these studies has primarily been on interactions between organic compounds. There have been relatively few studies involving metal complexes forming halogen bonds, and these have typically involved the ligands rather than the metals themselves. In this dissertation, the candidate applies crystal engineering principles to obtain metallopolymers by utilizing halogen bonding synthons. The primary aim was therefore to produce metallopolymers based on iodine X non-covalent interactions, where X is a halide ligand, iodine, bromine, or chlorine. However, the serendipitous formation of uncommon platinum iodine and palladium iodine interactions and an unusual polymeric chain containing potassium iodide interactions are also presented. The candidate particularly concentrates on the role that classic halogen bond donors such as iodine, 1,4-diiodo tetrafluorobenzene, and iodoform play in forming metallopolymers of different dimensionality. The dissertation opens with a clear and concise description of the background to the study, introducing the concepts of crystal engineering and non-covalent interactions with a particular focus on halogen bonding, although pi interactions, hydrogen bonds, and metallophilic interactions are also mentioned. The second chapter continues with the introduction, but with the emphasis on the methodology utilized during the project. In particular, the candidate gives an easily understandable explanation of the theoretical approaches used to investigate the nature of the non-covalent interactions in such a way as to place the results obtained within the context of the current literature. The results and discussion in chapter 3 sets the stage for the following chapters, which each consist of a completed article. 2 of these papers 1 and 3, have already been published, and the third has been submitted. These report the following noteworthy results. First of all, a series of platinum-2 halide cyclooctadiene complexes formed 0-dimensional, 1-dimensional, and 2-dimensional metallopolymers with the 3 classic halogen bond donors mentioned above. That's the iodine, the FIB, and the iodoform. Consideration of further interactions such as pi stacking allowed extension of the packing into 3 dimensions. Secondly, The differences in behavior could be explained on the basis of a variety of theoretical analyses: electrostatic surface potentials to probe the role of electrostatics and directionality, and a combination of electron localization functions, quantum theory of atoms and molecules, supported by analyses of the electron density and electrostatic surface potential minima to determine the nature and origin of the interaction. Thirdly, replacing the cyclooctadiene ligand used in the first study by 2 isocyanide ligands allowed the candidate to investigate the formation of chains of platinum or palladium complexes alternating with iodine molecules and held together by unusual I and II to IM interactions, in addition to iodine-iodine halogen bonds. Fourthly, the similarity of these iodine metal interactions to metallophilic platinum-platinum and palladium-palladium interactions moved the candidate to propose that they be considered as quasi-metallophilic interactions. Fifthly, a variety of non-covalent interactions were also found to stabilize a one-dimensional polymeric chain of cubic K4I4 units, with the potassium and nitrogen interactions playing the most crucial role, supported by iodine-iodine and nitrogen-iodine halogen bonding and potassium-iodine electrostatic interactions. The candidate successfully draws together these results from the separate papers and ends the dissertation by giving a cohesive summary regarding the insights gained throughout the project. As such, the work is interesting and novel and constitutes an important advance in the field of crystal engineering utilizing halogen bonding. The candidate and her supervisor are to be congratulated on work well done. May the fourth be with you.
Thank you so much. If anyone here has any critical comments to make on my dissertation, please ask the Custos for the floor.
Before going to the official end of this defense, I noticed that the candidate is missing one sock. So I want to hand you one sock.
Toby is free.
There has been no questions from the audience, so the defense is closed.